Good morning, everyone. Welcome to the OneClass channel. My name is Marlyn. I'm a second-year student at the University of Waterloo studying chemical physics with a minor in math. Today I'm going to be going through some high school level and college level chemistry problems. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tutoring. Okay, so for our first question, we would like to determine the molar mass of sodium carbonate. Okay, and so in order to calculate the molar mass, let's just recall what it is, and it's just the sum of the number of a specific atom, and that is going to be multiplied by the atomic mass of that atom. And so just as an example, if we had CH3, that would be 1 by 12.01 grams per mole plus 3 by 1.008 grams per mole. And that is going to give you the molar mass of CH3 as 15.034 grams per mole. And so a great way to do this is using this table that they've drawn up for us. Okay, and so here we have our element. Its atomic mass. So this part of the formula multiplied by the number of that atom, so this part, and then its total contribution. And so, in the question that they're asking for, it is Na2CO3. So let's fill in our elements first. We have sodium, we have carbon, and we have oxygen. We can go back to the atomic mass later. The number of sodiums we have are 2, number of carbons we have are 1, and number of oxygens we have are 3. So now let's fill in the specific atomic masses. And so the atomic mass of sodium is going to be 22.9898. The atomic mass of carbon is 12.0107, and the atomic mass of oxygen is 15.999. These are all in grams per mole. And so its total contribution for sodium is going to be 2 times the 22.9898, and that is going to give us 45.9795. For carbon, it's just 1 times the 12.0107, so it's just going to remain 12.0107. This is also in grams per mole, so it's just multiplying a constant by the grams per mole. And lastly, we're going to do 3 times 15.999, and that is going to give us 47.997 grams per mole. And so now, as I said, we want to add up all of these. And so if we go ahead and do that, we'll get that the total molar mass is 105.987. So we can just write out what we have. Yeah, and leave it like that. And that's your final answer. If you'd like to clean it up a little bit, we can give it to the appropriate number of significant figures because we had so many decimals here. Here I just happened to leave it at 105.987 if they had asked for six significant figures or 3 decimal places. So it depends on what format they ask you to give the answer in. Okay, next up, you're given the ammonia molecule and we'd like to determine whether it's polar or nonpolar and just explain our answer based on the electronegativity of nitrogen and hydrogen atoms. And so before we begin with the electronic or molecular geometry, we need to first figure out the Lewis structure. And so we begin by counting the valence electrons. We have 5 from our nitrogen and 3 by 1 because of the hydrogens. And so that's going to add up to give us 8 electrons to mess around with. Let's put our nitrogen as a central atom, because hydrogen can't be it, and surround it with our 3 hydrogens. So now we have a total of 6 electrons in the bonding pairs and 2 more electrons to put somewhere. We can't put them on hydrogen because it simply doesn't have the space. So it makes most sense to put them on the nitrogen. And now, since the valence electrons are all taken care of, let's double check on our formal charge. And so for the nitrogen, we will get 5 minus 3 minus 2, giving us 0 as we expected. And for the hydrogen, it will simply be 1 minus 0 minus 1, giving us 0 as expected. So our valence electrons are all okay, and our formal charge is okay. And so this is the correct Lewis structure. Now, based off of that, we can move on to finding the molecular structure. So we begin by counting the steric number. And that's the number of atoms or lone pairs attached to our central atom. And so we have 3 bonding pairs and an additional 1 lone pair. And so that's going to give us 4 as the steric number. And its notation will tell us how many bonding pairs there are compared to lone pairs. And that's going to be AX3E1. And so now we're going to pull up the VSEPR chart. Okay, and so we go to the total domains / steric number, and ours is 4 as we've determined. And then we will begin accounting for the number of lone pairs. So we have 3 bonding pairs and 1 lone pair. So its electron geometry will be what we first encountered, and that would just be the fact that it has 4 groups attached to it, so it's tetrahedral. And its molecular geometry accounts for how many are bonding pairs or lone pairs, and that is going to be trigonal pyramidal. And then let's go ahead and draw that out. Okay, and so now we can figure out the polarity by drawing out our dipoles and then seeing if they all symmetrically cancel out in order to give us a net dipole moment of 0. That would mean that it's nonpolar. And so the more electronegative one between nitrogen and hydrogen is going to be nitrogen. So just point all of those dipoles that way. And then between lone pairs and whatever atom it is, the lone pairs will have the higher electronegativity, so this will point upwards. And so now when we add all of these up, the angular components of these dipoles for the hydrogen will all cancel, yielding one vector pointing up, and then we also have the dipole pointing up towards the lone pair. Clearly these two will not cancel and hence will not be 0. What this now means is that NH3, ammonia, is going to be a polar molecule due to its non-zero dipole moment that is caused by the lack of symmetry in the molecule. And that's it for this one. So we've already made the drawing to support our answer. Next up, I want to predict the hybridization of the oxygen atom in water and draw a picture of its three-dimensional structure, and lastly explain why its bond angle is 104.5. Okay, so before we can get into the electronic or molecular structure, as usual, begin with the valence electron, so the Lewis structure first. And we will have 6 electrons coming from the oxygen plus 2 by 1 due to the hydrogen, and that's going to give us again 8 electrons to mess around with. We're going to place oxygen as our central atom because hydrogen can't be it, and just begin with 1 bond to each of the hydrogens. From there we'll have 4 electrons in the bonding pairs, and the only place the other 4 can go is going to be on the oxygen, so let's go ahead and place them. All of our electrons are now taken care of. Let's double check on our formal charge. On each of the hydrogens we are going to have 1 minus 1 yielding a 0. On the oxygen, we will have 6 minus 4 minus 2 yielding 0, 2. This is exactly what we had expected, and so this is the correct Lewis structure. So as usual now, we begin by counting the steric number in order to determine its electron geometry. And that is going to be the number of atoms attached to it plus the number of lone pairs. And so we'll have 2 bonding pairs because of the 2 hydrogens and 2 lone pairs because of the 2 lone pairs. And so that's going to give us a steric number of 4. But in its notation, let's account for the fact that 2 are bonding pairs and 2 are lone pairs. So that is going to be AX2, E2. So this is our bonding pairs, and this is our lone pairs. Okay, so now that we have this, we can pull up the chart. And we come down to the total domains, so that should be a steric number 4, and then we begin accounting for the number of lone pairs. And so our electron geometry will just tell us that the steric number is 4, and so that will tell us that it is tetrahedral. But our molecular geometry will account for which ones are bonding pairs and which ones are lone pairs, and that is going to be bent. And so now what that means is that we can just go and check what hybridization it is for steric number 4, and that's going to be sp3. A good way to remember this is that, okay, so first off, we have 1 s orbital per level, 3 p's, 5 d's, 7 f's. Each orbital can take 2 electrons. A good way to remember is just count the number of orbitals that you have. So 1 plus 3 is going to give us 4, and so that's going to represent a steric number of 4. Let's say we wanted to represent a steric number of 6 for whatever reason, then that would be sp3. So currently we have 4, and then we need to add 2d in order to get to 6. And so that's a quick way to just remember it just off of the steric number. And so our hybridization is going to be sp3. Okay, and then let's go about drawing that. You need to remember that all of these drawings here and where they have decided to place the lone pair is based off of the optimal structure that would minimize the electron-electron repulsion. And so it'd be best in our scenario to have our molecule in this configuration, which is one here, and then we have these two groups for our lone pairs. And so let's just redraw that and we just like turn it over so you can think about it. And so we have O and our two H's that are in the plane, and then those two. Yeah, and so what's going to happen is if it was tetrahedral, so let's say OH4 for whatever reason, then what would happen is we'd have a bond angle of 109.5 between everything. But then because of the fact that these two are now instead going to be electrons, so lone pairs, the lone pair of electrons are going to cause an extra push compared to the electrons in the bonding pairs. And so the electron isn't going to be as balanced out in terms of the repulsion forces. And so that's going to cause these angles to be bigger than they were supposed to be. And what that is going to mean is that the angle between the two hydrogens is going to be less than the idealized 109.5 degrees. And so usually in the question given, you can just leave it as less than 109.5. We are told that its bond angle is 104.5. That still makes sense because that is still less than the idealized 109.5, and that is caused by the fact that you have two lone pairs of electrons. Okay, next up, we would like to explain the electrostatic potential map for water and see how it corresponds with what we've been given here. And so in this map, in this map, we have it looking basically a bit like that. And then we have our actual structure in here. And so we need to understand how to read this. And so what the red means is that you have an area of high electron potential. So that just means that the area is going to be a little bit more negative because you have more electrons around it. And our blue means that we have a low electron potential. And so we can obviously explain this as being caused by not only the fact that oxygen, so A, we have the fact that oxygen is very much so more electronegative than the hydrogens. And so what that is going to mean is that in our bond, so let's take just one bond between the oxygen and the hydrogen, we're going to have the electrons more towards this side than the hydrogen because the oxygen has more pull on them. And so what that is going to mean is that the oxygen is going to gain a partial negative charge and the hydrogen is going to be left with a partial positive charge, and that's just because of the unequal distribution of electrons that's affecting them. And so oxygen will have a very high electron potential around it because it's almost taken the one electron from this hydrogen and the one electron from this hydrogen. Additionally, we have the fact that there are two lone pairs of electrons around the oxygen, and so that's going to increase its electron potential too. And so that explains why this area is going to be red due to those two factors. And the region around the hydrogens is going to be having a low electron potential because the electrons are simply closer to the oxygen due to its electronegativity. And so this will explain both the red and the blue. This just explains why it's that red compared to that of nitrogen. because nitrogen also has a higher electron potential, a higher electronegativity than hydrogen, and we can see that that's causing it to be slightly red due to these partial charges that we've talked about, but we can see it's not as red as it is in this scenario, and that's just because of those lone pairs of electrons. And that's it for this question. Okay, next up, we would like to explain what's going on with the solubility in these three cases. So benzoic acid being insoluble in water, acetone being soluble in hexane, and methylene chloride being, and oleic acid being soluble in acetonitrile. Okay, so we know that for solubility, like dissolves like. And so what that means is polar solvents will dissolve polar solutes, and nonpolar solvents will dissolve nonpolar solutes. And then lastly, we will have the case of how a mix of polar and nonpolar. And so you usually see this in our either substituted hydrocarbons or our organic compounds that aren't hydrocarbons, because they have things like oxygen attached to them that will be polar because of oxygen's electronegativity. And so substances like this can only dissolve in substances that are similar. So again, a mix of polar and non-polar. And so let's begin examining our cases. For the first case, we have benzoic acid. Benzoic acid is nonpolar, and we're trying the solvent of water, and water is polar. So of course, because these two are not alike, it's not going to dissolve, and so it makes sense that benzoic acid is insoluble in water. Next up, we have acetone, and acetone is going to be nonpolar. And we have hexane. That is again non-polar. And so we see these two are alike, and so we expect them to be soluble. And that's as we are told here. And lastly, we have methylene chloride. And this is going to be a mix, because you're going to have the hydrocarbon section that is not polar, and then you're going to have the chlorine attached to it, and that is going to be polar due to chlorine's high electronegativity. Additionally, we have oleic acid that's going to be the same. And so it's a mix, and we're trying to dissolve them both in acetonitrile, which is also an organic compound that is a mix. And so we will expect these two to be soluble in the solvent. And those are your final answers. sorry about that. Next up, we would like all of the acceptable lowest structures for C2H2Cl2. What are these structures and which of them are polar or nonpolar? Okay, and so with organic compounds that are in the format of C, so CnH, some function of N, and then you have a halogen. In order to figure out what it should look like, let's go about just replacing all of those halogens instead with hydrogens. And so in the case of C2H2Cl2, let's just think about what C2H4 would look like. And so C2H4, we know is going to be an alkene because it's following the general formula of CnH2n. And so we can expect this for C2H4. And so now, because we have two halogens instead of the two hydrogens, instead of the four hydrogens, let's just replace two hydrogens with the halogen that we have, so Cl instead. And if you'd like to just double check that this is all correct, we can count our valence electrons. And we know that we'll have 2 plus 8 plus 14. And that is going to give us 24 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Our valence electrons are all taken care of. Our formal charge on the carbon, we're going to have 4 minus 4, giving us 0. On the hydrogen, we're going to have 1 minus 1, giving us 0. And on the chlorine, we're going to have 7 minus 6 minus 1, giving us 0, 2. So clearly this structure is good to go. And so now that we have this structure, let's see if anything can be moved around. We know that it does not have to be these two chlorines on this one side, and so it can also be the structure looking like this. Let's just switch these two, right? And note this isn't the only other configuration other than this one. We can again switch two. And so now that we switched these two, instead of doing that, let's switch these two. And so we will have this structure. And so we haven't changed any of the formal charges. We haven't changed any of the valence electrons. We've just moved where the chlorines are. And so these are the three acceptable Lewis structures because all of them check out in terms of the counting. And so now let's go about drawing them. Both of these carbons are going to be sp3 hybridized, right? And so if we draw out each of their structures, it's going to be trigonal planar. And so we will have two trigonal planar looking carbons. And I know it's tempting to say, of course, what about like the case where we have two Cl's here and the H's here? We technically consider that the same thing as this at this level. And same thing, if you reflected this and had the two Cl's here instead, we'd also consider it the same as this one. And similarly, if we had the two Cl's here instead of here, we'd consider it the same. So these are our three structures that we can work with. And so now that we've drawn out the molecular geometry, let's see if the dipoles will cancel to determine which ones are polar and nonpolar. So in this case, we have this dipole pointing this way, this dipole pointing this way, this dipole pointing this way, and this dipole pointing this way. Again, chlorine is the more electronegative. Between carbon and hydrogen, carbon is the more electronegative. And then lastly, we will have okay, and so now we need to, let's actually draw the chlorine dipoles in a different color. And that's just because the magnitude of the dipole, which is determined by the difference in electronegativity between the carbon and the chlorine and the carbon and the hydrogen, they're going to be different. because the difference in electronegativity between carbon and chlorine compared to hydrogen and carbon is different. And so, okay, and so let's see if anything will cancel out exactly as it should. Okay, so in this case, we see that these two dipoles are equal and they're opposite in direction. So these two will cancel. Similarly here, they're equal and opposite in direction. So these two will also cancel. Here we see nothing is equal to the other one. And so these two, their angular components will cancel each other out indeed, but it'll still leave you with the same, component facing up, because that one hasn't canceled out. The same thing here, the two angular components will cancel out, but the one pointing up itself will not cancel. These two vectors obviously cannot cancel out. Sorry, these two dipoles obviously cannot cancel out, and so we'll have a non-zero dipole moment. And we know that that means that this molecule is going to be polar. Here we've seen that they do cancel, so this one is non-polar. And lastly, let's check on this one. It's going to be similar to what we had in this case, where yes, the angular components here will cancel, but it will leave you with this vector pointing to the right. Same thing here, angular components will cancel, but it will still leave you with this vector pointing to the right. And so these two obviously can't cancel, and you'll have a non-zero dipole moment. Let's just write out all of their net dipole moments. And so obviously that means that this one will be polar. And just so you know, this one has the name of, it's called cis. And that's strictly because these two are across from each other. This one is called trans. And that's strictly because these two are on the same side of the bond. If you consider this as a side and this as a side, opposite side, cis, same side, trans. And so as our final answer, we will have the trans molecule as polar, the cis molecule as non-polar, and this last one as polar. Okay, next up, we'd like the Lewis structure for CH2O. Let's count our valence electrons. 4 plus 2 plus 6. 12 electrons to move around. We know carbon will be our central atom. So the hydrogens, let's attach it to it. And then lastly, we have the oxygen. Let's put in all of our octets and see if we have enough. 2, 4, 6, 8, 10, 12, 14. So we have 2 extra electrons here. And we're going to fix that by having a double bond instead. And this just makes sense because carbon likes to have 4 bonds and oxygen likes to have 2. So just give them both what they'd like. Count our formal charge again. And so on the hydrogens, we're going to have 1 minus 1, 0. On the carbon, we're going to have 4 minus 0 minus 4, 0. And then lastly on the oxygen, we will have 6 minus 4 minus 2. And that is also 0. So our formal charges all make sense because the net formal charge is 0. And our valence electrons are all accounted for. So this is a correct Lewis structure. And so now we go about counting the steric number around carbon so that we can determine the geometry. And so we have 1, 2, 3 groups attached to it. So it's going to be 3, and none of them are lone pairs. So all bonding pairs, and so its notation would be AX3. If you go to the VSEPR chart, we just go to the total domain, steric number 3, 3 bonded atoms, and 0 lone pairs. And so what that is going to look like is we will have C attached to O, and then the H, and the H. And this is what it's going to look like. It will be trigonal planar in both its geometry, so its electronic geometry, and its molecular geometry. Now we need to determine its electron geometry. We found that it is trigonal planar. And now we'd like to find out what the strongest intermolecular force this molecule would exhibit. And so let's just list down these intermolecular forces so we can determine their various strengths and then determine which ones this molecule actually has. And so we have London dispersion forces. These are a form of van der Waal forces, and these are the weakest, and they're caused by temporary dipoles forming. And that's just going to be because of the electrons randomly being in places that would tend to form a dipole. We have dipole-dipole forces. So these occur in all molecules, including nonpolar and polar. We have dipole-dipole forces. And these are pretty strong. They are only in polar molecules, and they're a result of the net dipole moment being non-zero. And then lastly, we will have hydrogen bonding. And this is caused by a very high difference in electronegativity between hydrogen and nitrogen or oxygen or fluorine, I believe. And it is the strongest. And that is just caused by, because the difference in electronegativity is so high, the electrons are much closer to the nitrogen, oxygen, or the fluorine, and that gives a very high partial positive charge to the hydrogen and a very high partial negative charge to the oxygen, and that allows it to pull ionic species apart and isolate them. And so we just need to note which ones are possible in what we have. So London dispersion are possible because it's possible in all molecules. Dipole-dipole, in order to determine whether it's possible, we need to determine whether this molecule is polar. And so we begin by drawing our dipoles. And I'm just drawing these based on the electronegativity of these specific atoms. And so carbon has a higher electronegativity compared to hydrogen, and oxygen has a higher electronegativity compared to carbon. And so what that means is that these two, since they're equal, the angular components will cancel out, leaving with the dipole pointing up. And you'll also have the dipole pointing up towards the oxygen. Clearly, these two cannot cancel, and it'll be non-zero, meaning that the molecule is polar. So that means that dipole-dipole forces are possible. Next up, let's check on hydrogen bonding. So when it occurs when we have a high difference in electronegativity between hydrogen and nitrogen, oxygen, or fluorine. We do have hydrogens, but they're not attached to this oxygen. They're attached to carbon instead, which isn't listed here. The difference in electronegativity isn't strong enough to cause hydrogen bonding. And so this is not possible. So this isn't going to be in our molecule. And so between these two, which one is stronger? And that's going to be dipole-dipole. So dipole-dipole will be the strongest intermolecular force this molecule is going to exhibit. And then lastly, we are asked for the molecular geometry. And we've already determined it. It's the same as the electron geometry because of the fact that they're no lone pair. So it's going to be trigonal planar too. We want to draw its Lewis structure. We are told that there are no double bonds, no triple bonds, no expanded octets, and that is all that we are told about it. And so let's go about that. We have P4. Let's count its valence electrons, and it is going to be 5 by 4. And so we have 20 electrons to play with. Let's start with 1, 2, 3, 4, right? And let's just start with a single bond between each of them and fill in everybody's octet. Okay, and then let's count if our electrons all make sense. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have obviously more electrons than we need, but we are told that there are no double bonds and no triple bonds and no expanded octets. And so we can't place any double bonds or triple bonds like here in order to fix the electron issue. And so what we're going to do instead is connect the adjacent ones. And so let's start with 2. So that will leave us with 2 electrons on each. Yes. And so this one has made 3 bonds, leaving this one has made 3 bonds, leaving 1 lone pair. This one has made 1, 2 bonds, leaving 2 lone pairs. This one has made 3, and this one has made 2. Okay, and then let's see if that all works out. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So we still have too many. So how we can actually fix this is we're going to additionally connect these 2. And we're going to have to rewrite it to do that so it's a bit clearer. Because remember, we can't have any expanded octets and we can't have any double or triple bonds. And so now instead we have this looking structure with 1 bond between all of the phosphorus. And so this one has now made 3 bonds too. So it has 1 lone pair, 1 lone pair, 1 lone pair, 1 lone pair. Again, we count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So our valence electrons are all taken care of. Now we can check on the formal charges. For each of the phosphorus, it will be 5 minus the 3 electrons that they all have in bonding pairs, minus the 2 electrons they have on them. And so that's going to give us 0. That's as what we expected. And so this is going to be our final Lewis structure. Next up, we like to classify all of these molecules as polar or nonpolar. So we have H2CO. We begin by counting our valence electrons. 2 plus 4 plus 6, giving us 12. We previously found this molecule in a question, so we already know what it should look like. Just double check that it's correct. 2, 4, 6, 8, 10, 12. And all of our formal charges. On oxygen, it's going to be 6 minus 6, 0. Carbon, it's going to be 4 minus 4, 0. Hydrogen is going to be 1 minus 1, 0. So everything checks out for this Lewis structure. Next up, we go about finding its steric number. And carbon has 3 groups attached to it, so it's going to be 3. They're all bonding pairs. And so its notation will be AX3. Next up, you just pull up your chart. Total domains are 3. We have 3 bonding pairs and no lone pair. So this is going to be trigonal planar. And it's E electronic geometry and it's molecular geometry. And so let's just draw that out. And then to determine if it's polar or nonpolar, let's draw our dipoles. And so oxygen is more electronegative, carbon is more electronegative, carbon is more electronegative. These 2 will cancel, but not completely, to form 1 pointing up. And there'll be the 1 pointing up towards the oxygen. These 2 cannot cancel, and so it's going to be a non-zero dipole moment, telling us that this molecule is polar. Next up, we have CH3OH. Countervalence electrons, we have 4 plus 4 plus 6, giving us 14 electrons. we may begin with the 3 hydrogens in the carbon, attach the oxygen, and attach the last hydrogen. And so now we fill in all of our octets and double check all of our electrons. We have 2, 4, 6, 8, 10, 12, 14. Perfect, they all work out. Let's double check on our formal charge. On the carbon, it is going to be 4 minus 4, 0. On the hydrogens, all of them, it's going to be 1 minus 1, 0. And on the oxygen, it is going to be 6 minus 4 minus 2, 0. And so the formal charges all make sense. This is our correct Lewis structure. Now let's go about figuring out the steric number around carbon, and we also need to figure out the steric number around the oxygen. And so around carbon, it has 4 groups attached to it, so it'll have a steric number of 4. None of them are lone pairs, so that is going to be AX4. On the oxygen, we again have 4 groups attached to it, but 2 of them are lone pairs. So we have a steric number of 4 as well, but the notation will be AX2E2 to tell you 2 bonding pairs, 2 lone pairs. And so now if you go to our VSEPR chart, around the carbon, we have 4 total domains, which we've determined, and none of them are lone pairs. And so it's going to be tetrahedral. So let's first draw the groups around our carbon. And then we can go about drawing the tetrahedral nature of our oxygen. And so that one is going to be AX2E2 we've determined. And so it will have one pointing towards the side and one pointing up. And then you will have your 2 groups on it. So it looks a bit bent. In our drawing, we can just decide to ignore those 2 lone pairs and simply leave it like this. And so we know we can now begin to draw out our dipoles to determine whether it's polar or nonpolar. On everything. Okay. And so we know these 2 will add up to just form one vector pointing up. That will represent the difference in electronegativity between carbon and hydrogen. There's also one vector pointing up to represent the difference in electronegativity between oxygen and carbon. Next up, we have a vector pointing in this way to represent the difference in electronegativity between oxygen and hydrogen. And last up, we have additional vectors pointing in 2 directions to represent the difference in electronegativity between oxygen and the electron. So its magnitude will be different from this one's. And so obviously these will not cancel. They're non-equal, and there's nothing canceling out the ones that are equal in terms of them being opposite. And so this will be a non-zero dipole moment, which means that CH3OH is going to be a polar molecule. And just a quick note, yeah, it's just going to be polar in its entirety. If for whatever reason this region, the net dipole did cancel, but this region it did not, then it would be partially polar and partially nonpolar, but that's not the case. Next up, we have CH2Cl2, which we also did previously. So recall to get a general idea of what it should look like, just replace the halogens with hydrogens and it becomes CH4. We know that CH4 would look like this. And then we just replace 2 hydrogens with chlorines. Now, depending on which one you pick, you will have different molecules. And so if we decide to replace these 2 with chlorines, we'll get this. If we instead decide to replace these 2, we get this. And if we instead decide to replace these 2, we get this. Now I've already drawn it how to technically look in terms of the trigonal planar notion. If you want to get there on your own, you just need to notice the steric numbers on each of the carbons. Each carbon has 3 groups attached to it, so they will both be AX3, steric number of 3, and none of them are lone pairs. And so when you go to the VSEPR chart, AX3, 3 bonded atoms, 0 lone pairs, and so it's going to be trigonal planar. And you can see that this side is trigonal planar and this side is also trigonal planar, so the two add up to look like that. Sorry, let's put our valence electrons around the chlorines. Okay, and then now that we have the geometry, let's go about the dipoles. So we have a dipole pointing that way. Okay, and then let's now double check if anything cancels. And so here they cancel in terms of horizontally, but vertically they don't. And so you're left with just one vector pointing upwards. Here again, they cancel in terms of horizontally, but vertically they don't. And so it also leaves you with a vector pointing upwards. These two obviously cannot cancel, so we'll have a non-zero dipole moment here. And so this version of CH2Cl2 is polar, because all of these 3 structures are allowed. Next up, let's see if these two cancel. Horizontally they do, vertically they do, horizontally they do not. And so left with a vector pointing right. Same thing here, we'll be left with a vector pointing right. These two cannot cancel, and so we'll have a non-zero dipole moment, so it'll be polar. Here, these two do cancel. They're equal and they're opposite, so they cancel. These two are also equal and opposite, so they cancel. And so we will have a 0 dipole moment, and this one will be non-polar. And so depending on which of these 3 versions you have of CH2Cl2, you'll get a different answer for whether it's polar or non-polar. But if you're asked to draw them all out and label each individual one as polar or non-polar. Lastly, we have CO2. We can count our valence electrons. We'll have 4 plus 12 yielding 16 electrons to take care of. Carbon as our essential, oxygen and oxygen. If we fill in everybody's octet, we'll have 6, 8, 10, 12, 14, 16, 18, 20. So obviously we have too many electrons. We know carbon likes to make 4 bonds and each of the oxygens like to make 2 bonds. And so we can go ahead and just give everybody what they want and see if the valence electrons make sense that way. Now we have 2, 4, 6, 8, 10, 12, 14, 16. Our valence electrons all make sense. Let's double check on our formal charge. On the oxygens, we'll have 6 minus 4 minus 2, giving us 0. And on the carbons, we'll have 4 minus 0 minus 4, giving us 0. And so both of our formal charges make sense, our valence electrons make sense. So this is obviously the correct structure. Now let's count the steric number. The steric number is there are only 2 groups attached, so it's going to be 2. And its notation will be AX2 since we have no lone pairs and 2 bonding pairs. Go check the chart. Steric number of 2, 2 bonded atoms, 0 lone pairs, and so it's going to be linear. Next up, let's go about drawing our dipoles. And so we'll have 2 equal and opposite dipoles pointing towards the oxygens. Obviously, they will cancel. And so we'll have a 0 dipole moment, meaning that this molecule will be non-polar. And that's it for this question. Okay, next up, we would like to talk about valence electrons. So valence electrons are the electrons occupying the last shell And so how this is typically described at the high school level, if you're using the planetary model, is we have our nucleus, and then we have all of these levels that can hold different amount of electrons. The first one can hold 2, the next one can hold 6. It's 8, yeah. And so on and so forth. And so if we have, for example, carbon that has 4 electrons, then we'd have 2 in the first layer, and then we'd have another 2. Sorry, it has 6 electrons, so we'd have another 4 on this last shell. And so these 2 electrons, we don't count them as valence electrons because their shell is full and they're taken care of, is how you can imagine. And that's because they won't be participating in reactions when they occur, because it's only this last shell whose electrons will be participating typically. And so we would count the valence electrons for carbon to be 4. And so now let's do nitrogen, which is what we were asked for. The theory remains the same no matter which model you're using, because they're just trying to present you with the same information in different ways, some of which aren't accurate, such as the planetary model. Our nitrogen, we know it has 7 electrons in total, right? And so if we continue to use the planetary model, we'll have 2 on the first layer, and then we'll have 5 on this last layer. And so what that means is that on this last shell, we have 5 electrons, and so that is going to be our number of valence electrons. Next up, we're told an atom has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p2. How many valence electrons does this atom have? And so this is when you're using the more accurate model dictated by, of course, quantum mechanics. And so if we use that, and the reason why it stays the same is that you can consider the 1s2 as that first layer that only had 2 electrons. You consider the 2s2, 2p6 as that next layer that permitted 8. And then you just continue like that. And so if we have 2s2, 2p6, then we have 8 electrons here. And then lastly, we have 3s2, 3p2. And so that's also going to be another shell, and we have 4 electrons. And so we'll have 1, 2, 3, 4 on the last shell. So you have 4 valence electrons. Alternatively, you can write it out in the more accurate way, where you write out the orbitals. So you have 1s, 2s, 2p, 3s, 3p. And so we'll have the 1s2, 2s2, 2p6, 3s2, 3p2. And so we see these ones are all filled up. This level isn't yet. And so we have 1, 2, 3, 4 electrons on it. So we have 4 valence electrons for whatever this is. If you'd like to figure out what it is, just count down the periodic table. So 1s2, 2s2, 2p6, 3p2, 3p2. So this is going to be silicon. And that's it for this question. Yeah. Okay, we want to write down equations corresponding to the following. So I need to understand the words that they're using. So the ionization energy, which is typically just written IE, is defined as the minimum energy to remove an electron. To remove the outermost electron. but we're told we want the fourth ionization energy. And so what that is going to mean is we want, like in the case of Se, we want to go from Se3 plus to Se4 plus an electron. And the reasoning for this, the reason why it isn't just Se plus to Se2 plus E is that this would be our second ionization energy. Our first ionization energy would be going from the neutral state to the state. So this is our first, that's our second, and our third one would be going to this. So this is our third, and this is going to be our fourth. A good way to just remember it is notice the 4 is leading to a 4 plus, second is leading to a 2 plus, the first is leading to a 1 plus, and the third is leading to a 3 plus. Additionally, we have the electron affinity, and that is defined as the energy released when an electron is added. To atom or molecule in gaseous phase. Okay, so for our first question, we asked for the fourth ionization energy of Se. So you know we'll want to get Se4 plus since it's the fourth, plus an electron, and then we just balance out the charges on both sides. Here we have a total charge of 3 plus, so you expect a total charge of 3 plus on the other side too. Let's do D, since it's also asking for ionization energy. We asked for the ionization energy of magnesium, and it's just magnesium and not told what number of the ionization energy, and so we're just going to assume it's the first. And so we know that that would like to produce Mg plus an electron. And it's coming from Mg. Double check that the charges are balanced on both sides. Sorry about that. And this is correct. And then lastly, let's do our electron affinity questions. And so we have S minus. And we're asking for the electron affinity, which means the energy released when an electron is added. So that means that we're going to add an electron. And that now is going to produce Se2 minus, 2 minus, and S. And just note that here I knew that because this side has a total charge of 2 minus, so this S should have a total charge of 2 minus 2. And then we have C, which is Fe3 plus, it's electron affinity, so you add an electron. Yeah, so a total charge of 2 plus, total charge of 2 plus on both sides. And that's it for this question. We like to find out the names of these two ions. So O2 minus, we know that the atom is oxygen, which is O. I minus, we know the atom is iodine, which is I. Now, to account for the fact that these two have negative charges, we add the suffix "ide." And so instead of oxygen, you will drop this and it will become oxide. So instead of O, we have O2 minus. And instead of iodine, you drop this and it becomes iodide. Instead of I, you have I minus. So the two names are O2 minus is called oxide ion, and I minus is called the iodide ion. And that's it for this question. Next up, we'd like the molecular shape of NCl3 and the electron group geometry around N. Is it polar or nonpolar? And so again, we need our valence structure, and that is going to be 5 plus 3 by 7. Our valence electron, so that's going to be 21 plus 5, and so we have 26 electrons to play with. So let's put nitrogen as our central because it can make the most bonds. Start with 1 bond to each of the chlorines. Fill in all of our valence electrons and see if we get our 26. All of our octets, my apologies. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All of our valence electrons are accounted for. Double check on our formal charges. Chlorine, we have 7 minus 6 because of the lone pairs, minus 1 because it has 1 electron in this bond. That's going to give us 0. On the nitrogen, we'll have 5 valence electrons minus the 3 electrons in each of these bonding pairs, minus the 2 lone electrons, and that's going to give you 0, 2. So our formal charge makes sense. Our valence electrons are all accounted for. This is the correct structure. Next up, to get its geometry, we need to think about the steric number. So how many groups are attached to the nitrogen? We have 3 groups because of the 3 chlorines, and then 1 group because of this 1 lone pair. So that's going to be 4, and its notation will be AX3E1, bonding pairs, lone pairs. Go to the Vesper theory. The total number of domains are 4, and so the version of it with no lone pairs is what is going to be our electron geometry, and it just doesn't account for the fact of which ones are in bonding pairs and which ones are lone pairs. And so its electron geometry is going to be tetrahedral, but its molecular geometry will account for which ones are lone pairs and bonding pairs. And we know that we have 3 bonding pairs and 1 lone pair, so it's going to be trigonal pyramidal. Okay, and then we are asked if it is polar or nonpolar, so let's draw it out the way that the structure should look. And then let's draw our dipoles. Lone pair is always more electronegative. Chlorine, chlorine, chlorine. And so we know these 3 will add up in a specific way to give you a dipole moment facing downwards, and this one will give you a dipole moment facing upwards. It would be natural to expect them to cancel, but you need to remember that the difference in electronegativity between nitrogen and chlorine and between nitrogen and their lone pair are different. And so yes, they're in opposite directions, but they will not cancel out completely to give you a 0. It'll cancel out to give you a positive or a negative. That isn't our business right now. It just matters that it is not a 0, which means that this is going to be a polar molecule. And that's it for this question. We'd like to draw the Lewis structure of CH2N2 and include any formal charges. Okay, so you'll notice that this isn't a halogen, so it can't do what I had described for a CH2Cl2. If for whatever reason we did decide to do that, let me just prove that it'll just yield something incorrect. So we'll start with C in the middle, H, 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 and then we'd replace 2 with what we actually have. And then we just need to remember our valence electrons. We have 2 plus 10 plus 4, yielding 16 electrons. Let's fill in everybody's octet. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So clearly this does not work. If we start talking about double bonds around the carbon, let's see if that does work. We have 2, 4, 6, 8, 10, 12, 14, 16. The electrons all make sense, but this would imply an expanded octet around the carbon, and that is not the best. And so instead of having this structure, because we technically cannot have an expanded octet around carbon, doesn't have enough orbitals to permit it. And so instead, let's indeed leave our two hydrogens attached to the carbon, attach the nitrogen, and then attach another nitrogen to that nitrogen. Fill in all of our octets. And we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Remember we had 16 valence electrons. And so obviously this still not is permitted. Let's put a double bond around these two. Because carbon likes to have 4 bonds, nitrogen likes to have 3. Just give them both what they want. 2, 4, 6, 8, 10, 12, 14, 16, 18. So this is clearly still not enough. And so let's have another double bond here. Because again, we had too many electrons. And that will leave us with this structure. We have 2, 4, 6, 8, 10, 12, 14, 16. Our valence electrons are all taken care of. Let's check our formal charges. On the hydrogens, we have 1 minus 1, 0. On the carbon, we have 4 minus 4, 0. And on the, let's call this nitrogen 1, nitrogen 2. On nitrogen 1, we have 5 minus 4, leaving a positive 1. And on nitrogen 2, we have 5 minus 4 minus 2, leaving us with a negative 1. So we'll have a negative charge here and a positive charge here. And the question mentions resonance structures. So what that means is, can we move any of the electrons either in lone pairs or in these double bonds into a configuration that is different from this one, but still maintains this formal charge of 0 and still maintains the 16 valence electrons? And indeed that can be done if instead of having this, we had C, H, N. You move the 2 electrons in this double bond into a bond between these 2 nitrogens. And then you move one of these lone pairs to the carbon instead. So you still have the same number of lone pairs, the same number of bonds, the same number of electrons therefore. Let's double check that our formal charges are all okay. So the formal charges are allowed to move, but the net has to remain the same. And so on our hydrogen, we'll still have 1 minus 1, giving us a 0. On our carbon now, we will have 4 minus 3 minus 2, and that's going to give us a negative 1. So we can see the negative charge has moved to the carbon. Yeah, and then let's double check on our nitrogen. So again, we have N1 and N2. On nitrogen 1, it is going to be 5 minus 4, leaving a positive 1. And on nitrogen 2, it is going to be 5 minus 3 minus 2, leaving a 0. And so we'd be left with this structure. Is there anywhere else where we can move any electrons? The answer is no. We know that if we have the lone pair on this nitrogen, then we get the incorrect, the valence electrons don't check out. That's what we had initially. And if we have the lone pairs on hydrogen, that simply doesn't make sense because hydrogen can't have that many electrons on it. So our 2 structures are going to be these 2. And on this one, the charge there we go. And so those are our 2 resonance structures, and that's it. Next up, we'd like the molecular geometry of COCl2. Count our valence electrons. 4 plus 6 plus 14. That's going to give us 24. Carbon is obviously our central. And then let's just attach everything to it. Fill in everybody's octet. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We have too many electrons. Now we need to figure out, okay, where are we going to place a double bond? Would we like to place it between any of the chlorines? Ideally, no. We know chlorine likes to make one bond, and that would minimize its formal charge to be 0. So instead, and additionally, we know oxygen likes to make 2 bonds. It currently has 1. Carbon likes to make 4 bonds. It currently has 3. And so what we can do is place a double bond between them, because that would minimize both of their formal charges, and leave the chlorines alone because they're currently okay. Double check your electrons again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Valence electrons I'll check out. Double check our formal charge. On the carbon, it's going to be 4 minus 4, 0. On the oxygen, it's going to be 6 minus 4 minus 2, 0. And lastly, on the chlorine, it's going to be 7 minus 6 minus 1, 0. So our formal charges all check out. Our valence electrons check out. So this is obviously the correct Lewis structure. Now let's go about finding the steric number. Carbon only has the 3 groups attached to it, no lone pairs, and so its steric number is going to be 3, and its notation will be AX3 because there are 3 bonding pairs and no lone pairs. We come back to our Vesper theory. Total domains are 3, so its electronic geometry is trigonal planar. Its molecular geometry is going to be the same because there are no lone pairs. So it's also going to be trigonal planar. So the answer for our question is the molecular geometry is trigonal planar. And that's it for this question. Okay, and then lastly, we would like to figure out the molar mass of ammonium nitrate, calculate the mass percentage of nitrogen in ammonium nitrate, figure out how many kilograms of nitrogen would be in a 10-pound bag of ammonium nitrate, and how many pounds of ammonium nitrate would be in 1 pound of nitrogen. So to figure out the molar mass, of course, we're going to sum the number of a specific atom multiplied by that atom's atomic mass. Think about it like that. Okay, and so let's draw a table again if we'd like. Okay, and so you're going to have our element. We're going to have the number of that atom, and then we're going to have the atomic mass. And then that is going to multiply to become its contribution. And so first we have nitrogen, we have hydrogen, and we have oxygen. The number of nitrogen, 2. Number of hydrogen, 4. Number of oxygen, 3. The specific atomic masses, you can find them easily on Google. We're just going to put down 2 0 decimal places. 116. And so its total contribution is going to be 28 plus 4 plus 48, and then it's going to give us a total atomic mass, sorry, a total molar mass of 80 grams per mole. And this is for NH4NO3. Next up, they ask, what is the mass percentage of nitrogen in ammonium nitrate? And we're going to calculate this using the molar mass of ammonium nitrate and the atomic mass or contribution of the nitrogens. And so the mass percentage is going to be the contribution of whatever atom we have over the total molar mass of our substance. And so since we're looking for the, times 100 because it's a percentage. Since we're looking for the mass percentage of nitrogen, we're going to do contribution of nitrogen, which is 28, over the total molar mass, and that's going to be 80 times 100. And that is going to give us a mass percentage of 35%. What this means, you can think about it in terms of actual masses, that if you had 100 grams of ammonium nitrate, 35 grams would be nitrogen. So for the next question, we're going to use this fact, and we have 10 pounds of ammonium nitrate. We want to figure out how many kilograms of nitrogen we have. So first and foremost, we are going to need to convert that 10 pounds into kilograms. The conversion is done here. So 10 pounds by so since 1 kg equals 2.20462 pounds, that means 10 pounds is going to be equal to 10 over that number. And that is actually going to give us roughly 536 kilograms, and that this is going to be equal to 4,536 grams. Okay, and so since we know that for every 100 grams of our substance we have 35 grams of nitrogen, we should get the same ratio if it's out of 4,536 grams. And so the ratio is going to be and so we're going to get 1587.57 grams, and we can just rewrite that as 1.5876 kilograms. There's a bit of rounding error just because of decimals dropped. But yeah, and so in 10 pounds of ammonium nitrate, we have 1.59 kilograms of nitrogen. And now we're going to in a way do the reverse. We know how much nitrogen we have. We're trying to find out how much ammonium nitrate we have. And so again, if we have 35 grams of nitrogen, we know that we should have 100 grams of ammonium nitrate, and we're told that we have instead 1 pound of nitrogen, and we're trying to figure out x. And so we are going to have x is equal to 100 over 35. And that is going to give us, we have 2.86 pounds. And that's it for this question. And that is, sorry. And those seem to be all the questions that I have for you today. I hope you enjoyed today's Q&A. If you'd like to be notified of when we post, be sure to hit the subscribe button and the bell right next to it so you do get notified. If you'd like to post questions of your own, be sure to check out the links in the description so you can get access to the OneClass page. This has been Marlyn from OneClass, and I hope to see you next time.